discussed before, we talked about products actually. In this case, we will focus on the processes related to those products. Again, you see the name and the face and the voice of me and Maria Telli, University of Bologna. Of course, there are several partners, several people working on this along 4 years, the last 4 years. Well, the basic idea here was to mix together biological, biotechnological process and chemical approaches to obtain targeted bio-based products. So on one hand, we work around, as I told before, around an improvement and change, a modification of the anaerobic digestion processes to obtain some given bioproducts. And on the other hand, we work on a cascading of biotechnological and chemical physical processes to convert part of the agro-waste and mix together some of the molecules. So one example was to put together the fillers, the lignocellulosic fillers coming from, for example, wine roots, together with the polydrosylcanoates to have biomaterials, to have biocomposites. So we will see now that we work on several directions actually. So coming to the biofuels I discussed before, clearly there was the idea to change in some way the conventional anaerobic digestion processes, which is a typical anaerobic process where you put agro-waste inside, and after a given time, let's say 30, 40, 60 days, what you obtain is biogas, which can be used directly, burned to obtain energy, or you can upgrade and obtain biomethane. In this sense, the innovation part was on one hand dedicated to two-stage processes where you have the production of hydrogen in the first step and again methane in the second step. So you can produce bioethane. It's something we work with Innoven here in Italy, with INRA in Montpellier, while the guys in Rome at Sapienza, they work basically on the bioelectrical conversion of part of the CO2 into the biogas in order to upgrade the biogas to something more similar to biomethane compared to what is already in the market now, which is a sort of chemical physical processes to actually remove CO2. Here the idea was to convert CO2 into methane in order to increase the presence of methane into the biogas. So we also work on the pre and post treatment, like the guys at the NTUA in Athens, in Greece, in order to actually enlarge the portfolio of possible feedstock for anaerobic digestion. Of course, anaerobic digestion today is basically working on wet byproducts actually. Of course, imagine you can also treat straw or other lignocellulosic material. Of course, you have to destroy part of this lignocellulosic backbone of the material. So you need some alkaline pretreatment, some energy, some chemicals before and after the process in order to partially destroy this material and make sugars accessible to bacteria to obtain other biogas. And the same was done at a larger scale from the guys in Denmark, both Aalborg University and Biovantage, which work with AD Booster, which is the application of a wet oxidation process where you can again pre-treat or post-treat part of the digestate and recycle it back to the digester. And it's quite clear if you look at the graph here on the right side. It's quite clear when you treat this material, you have a clear increase in terms of methane production. So again, can you close the mic, please? Thank you. So there is again the opportunity to improve the process yields, which is very important because you can actually enlarge the portfolio of biomass you can imagine to treat into these digesters. Actually, again, we talk about biochar, which is coming from the connection of anaerobic digestion together with pyrolysis approach. As we said before, you can produce, for example, bio-oil or syngas, which can be used as a biofuel. But of course, you have also an increased capability of using the digestate. You produce biochar, which can be used as an amendment actually for improving the quality of soil, which is a very important part. You have to imagine that in any case we are trying to close in a loop, so all the material, residual material coming from this biotechnological approach, of course, should come back to the land. So it's very important also this part. Another very interesting part, we work together with Innoven and Sapienza of Rome. The basic idea here was to ferment this agro-waste to produce volatile fatty acids, take a volatile fatty acids and transform these into polyhydroxyl canoates, the granules, the white granules that Anna Maria showed us in the previous presentation. Here you see the final sludge, and after extraction and purification, what we obtained was this one. Not still 100% happy with this. We are still working on this to improve the quality of the final material, but very important, we were able to prove the concepts actually. So it is clearly possible to obtain PHA through this way. It's a given interesting quantity actually in this moment. So we are in the direction to have enough material to work with the industrial machine to prove that this biopolymer can be, as it was in the question before, can you work it, can you blow it, do you have technical mechanical properties? Yeah, it's something we are trying now. I mean, it's something we are trying to demonstrate in this period actually. Again, PHA was demonstrated by the unit research unit in Lisbon at EBET that okay, PHA can be used also, can be produced also in another way. For example, using purple bacteria. The purple bacteria again, they use volatile fatty acid again, and of course they can produce PHA inside the bacteria, but you are eliminating, for example, the aeration cost. You don't need a large amount of substrate, of volatile fatty acids, and most of all, you are using something which is low cost, which is the sunlight. So again, we demonstrated the possibility to have new processes on the chain which can help us to have this new material. So coming to the other processes, again, I give it a hand to Anna Maria Celli, who is going to explain you this very sexy thing.
Okay.
Here, very complicated, a lot of rows, but I think she can explain you how it works.
Yes, I try. I would like to show you some cascading processes we have developed, starting from winery waste to obtain different biomaterials. This is an example of a fully valorization of an agro-waste, and we tried to develop sustainable processes in order to valorize all the waste. So, starting from wine pomace and wine shoots, we reduced this agro-waste in powders, and these powders can be used to prepare a composite, biocomposite based on polyhydroxyalkanoate produced as David described. Then wine pomace and wine shoots reduced in a powder can be also a source of bioactive molecules. Indeed, we develop the extraction of these bioactive molecules, and so we have different pathways. Starting from the left, first of all, we obtain a mixture of polyphenols. These polyphenols, as already described, are characterized by antioxidant and also antibacterial properties, and so these polyphenols have been used for an active packaging, as already described. Moreover, bioactive molecules can be also specific molecules useful to obtain specific materials. For example, I described the possibility of extract from agro-waste some specific kind of polyphenols such as tannins, and the tannins can be can become building blocks for new resins. Moreover, some other specific molecules can be the object of the research. For example, in one grape pomace, it's possible to identify some amount of vanillic acid. And this vanillic acid can be very interesting to obtain aromatic building blocks used to obtain bio-based PET-like polymers and copolymers. But after the extraction, a solid residue is produced. And also these solid residues can be used, as described in the right part of the slide, can be used to produce other biocomposites also based on PHA. So we start from an agro-waste. We can be used directly this agro-waste for biocomposite, or we can extract interesting active molecules and use the solid residues after the extraction to produce new biocomposites. So I will try to explain some details of some of these research line. For example, in the next slide, David. Yes, the extraction of polyphenols have been carried out, starting from two kinds of wine pomace, red pomace and white pomace, and two extraction methods have been compared: solvent-based extraction and pressurized liquid extraction. Moreover, both methods have been optimized, and the solvent-based extraction based on the use of acetone was selected as the best process for the recovery of these polyphenols, bioactive molecules, from both red and white grape pomace. And it was interesting to observe that a complex mixture of polyphenols was obtained. For example, in the next slide, it's possible to observe the composition of this mixture of materials, of molecules. The composition is very complex, but in any case, these mixtures of components are characterized by antioxidant and antibacterial properties. So these mixtures can be directly used for active packaging. Moreover, if you click, David, okay, another time. Moreover, we obtain also solid residues of extraction as already described. In the next slide, there is a description of the production of active packaging. Indeed, the polyphenols at the beginning were blended with the bioplastics, for example, polylactic acid, but also PHA, for the preparation of antibacterial food packaging. And the polyphenols maintain their ability to and confer antioxidant and antibacterial properties to the product. Then, in order to minimize the use of polyphenols, a coating strategy has been chosen, and polyphenols extract. Sorry. Polyphenols extract have been coated, deposited on a material sheet and tray, and also in this case, it's possible to obtain materials, products characterized by antioxidant and antibacterial properties. So these can be potentially very interesting results for application at industrial level. Moreover, in the next slide, David.
Sorry.
Okay, here the description of the production of biocomposites. We have used wine shoots, grape pomace, solid residues of polyphenols extraction, but also waste obtained from the extraction of starch from potatoes with potatoes. The solid residues also in this case have been used. All these residues have been reduced in powders, and the powders have been mixed to the polymers in, for example, Brabender mixer or in extruder. This process is very friendly, eco-friendly, because no solvent have been used, no additives, directly this powder and polymers. And then the materials have been reduced, for example, in different kind of samples, for example, film sheets and so on. So this procedure is really very easy. The materials are homogeneous. The properties of the original polymeric materials are maintained. There is, for example, is slow decrement of tensile properties, but this decrement is surely very moderate. The amount of fillers added reach a percentage of 20–30%, so in weight. So this can be a very interesting strategies to decrease the cost of the polymeric matrix. So in the next slide, these are the conclusion. We have shown an example of a circular bioeconomy. Instead, we start from agro-waste. By anaerobic digestion, it's possible to obtain PHA, but from agro-waste, we can also extract polyphenols. We can also obtain lignocellulosic fillers, and using PHA mixed with the polyphenols, we can obtain active packaging. Using PHA with lignocellulosic fillers, we can obtain biocomposites. Both these products are degradable, so we can obtain from them compost that return to agriculture, and so the loop is closed. So thank you, and see you the next step.